All right, so let's do some quick examples with this centripetal force stuff that we looked at last time. So again, if we remember, what we were able to derive was that when we have uniform circular motion, our acceleration is mv squared over r, sorry, is v squared over r, which means that our centripetal force, right, the net force acting on our object must be mv squared over r, right? So again, this isn't some extra force that we're going to have acting on our object. We're going to say, okay, we're going to do our Newton's laws. We're going to draw our free body diagrams. We're going to add up all of our forces. And if our object is undergoing uniform circular motion, then I know that this must be what the magnitude of the net force is on the thing. And then, of course, the direction of it will just be pointing straight in towards the center of the circle. So let's do a couple examples with this. Let's say we'll do some simple car examples. We'll put some numbers to kind of the stuff we were looking at last time. So let's say for this first part, we're going to find the centripetal force F of C exerted on a 900 kilogram car going around a, going around a 500 meter radius turn at 25 meters per second, right? So again, we know it is, since we are going around this turn, even though we might not complete a full circle, for this time we are effectively undergoing this uniform circular motion, right? Even if I only turn a few degrees, right? If that turn is circular, which is what we're going to approximate this turn to be, then regardless of how far around the circle you go during that time where you are moving in this circular motion, you don't have to actually make one full revolution or anything like that to still have your object undergo uniform circular motion. So this is what we want to do. First, we'll find this, and then the next part, this is just an example from the book that I'm just going to put some numbers to and kind of work through. We're going to say find the minimum coefficient of static friction, the minimum mu sub s coefficient of static friction needed to keep the car from slipping. So of course, as we all know, if you take a turn and you go around it too quickly, you will slip off the road. Hopefully you don't actually do this, but of course it is the friction between the road and your tires that is keeping you from doing that, right? And of course you've probably heard it, right? You've probably heard someone else do it if you haven't done it yourself. When the tires start to slip, they start to screech really loudly, right? So at that point they have they have surpassed the force of static friction between the tires and the road, and now the tires are actually sliding on the road. It makes an awful noise. So what we're going to need to find is what the minimum coefficient of static friction between the tires and the road is in order to prevent that from happening. So that's going to be the first part. Second part. So for the first part, though, let's just go ahead. Let's figure out what this force is. So let's draw our free body diagram again. Make sure we're all on the same page. So here's kind of the back view of my car. So again, we're saying the car is traveling into the page, right? Going in this direction, and it's turning to the right as it does so, and we're looking at it from the back. So my forces on this, we have mg pulling it down, we have the normal force pulling it up, and of course it must be friction, right, acting parallel to the surface, right, parallel to the surface, and it opposes the motion, which is a little awkward in this case when you have tires on the road. So obviously the car is moving to the right. Friction is what's pulling it to the right, but the way you can think of it is this. It opposes the motion between the two surfaces. So if we didn't have friction, which way would the car slide? It would slide off to the left of this turn, right? So the wheels are trying to slide to the left, so friction is actually pulling them to the right. So this is the overall picture that we have. So we can say this. If we look in the y direction, we know right away our normal force is just going to be mg, nice and simple. And in the x direction, we know then that our frictional force must be equal to mv squared over r. So we don't need to worry too much about the details of this friction just yet. That's for part B. So for this first part, though, we can just say the mass of the car, is 900 kilograms times the speed, 25 meters per second, square that, divided by a 500 meter radius, and what we get for our force is about 1125 newtons, right? So this is the overall magnitude of the force that's actually pulling this car to the right, 1125 newtons. So with this, that's a part A. So now we can figure out what is the minimum coefficient of static friction needed to keep the car from slipping. Well, what is F? You know that F has to be equal to mu times the normal force. So we can say this. We can say we have mu mg, right? Mu times the normal force must be equal to mv squared over r. And so then our coefficient of static friction would be what? So we can cancel out these m's. We can divide by g, and our mu will end up being mu equals v squared over rg. Plug all of those numbers in, and we get as a coefficient of static friction of about 0.13. So in this case, right, we're taking a pretty wide turn, right? The radius of the turn is 500 meters. So we do need a relatively small coefficient of static friction to pull us around this turn. Usually when you have tires on pavement, your coefficient of friction will be around like 0.8 or 0.9, something like that. If it's wet pavement, it'll maybe be like 0.2 or 0.3. So either way, even if even if it's raining outside, we should still be able to go around this turn at this speed, right? So what we're saying again, this is the minimum coefficient of static friction necessary. Obviously, if the coefficient of friction between the tires and the road is higher than this, then we'll be fine, right? If it's able to do exert a stronger force, it doesn't necessarily mean that it will. But it will, anything higher than this will still get us around. But of course, we can also see from this, when we're on a flat turn like this, we actually do need some kind of friction, right? If we're actually trying to turn on a flat road, we have to have some kind of friction, or else it is not possible to make it around the turn. So this is usually the case. You probably turn on these roads, if you're just driving through residential streets. But if you're on the highway, you're actually going at a pretty decent speed, which, 25 meters per second, it's roughly 50 miles an hour, a little bit faster. You're probably going to be doing this somewhere on the highway, right? And something you'll notice is that the roads are built a little bit differently in that case. When you actually take turns on the highway, what is different? Well, the picture is slightly more complicated, but there's a very good reason for it. So if we were to look at this again, right, we're going to do this car going around a turn. Let's do it in a couple different ways. Let's look at a couple different cases. So when we take this turn on the highway, what we'll notice is that the road is actually angled, right? It's a banked turn, usually anyway. And so this is now the back view of my car, right? So now my car is still again going into the page and turning to the right in this picture. So the road that we're on is banked, right? We have this angled turn. As it turns out, the reason for this is because this is actually, when we bank these turns, it is going to help the car actually make it around the turn, right? So this is a very good reason for the actual engineering behind why we do this. When you have this kind of increased angle here, you actually can essentially you're taking use of the normal force to kind of help push this car around the turn. So let's take a look at that, and let's actually take a look at the case with no friction, right? So before we could see, obviously, in this case here, if we have no friction, right, if our mu is 0, we're never going to turn, right? Or we're never going to be able to actually make it around this turn. Whereas with the case of these banked turns, if we have a coefficient of friction of 0, we can still make it around the turn, right? So again, just to kind of illustrate this idea that this banked road that we're on, this banked turn that we're moving on, is able to actually push us around the turn all by itself. So if we draw my case for this, so again, this is going to be, make sure I label this correctly, banked turn, no friction, right? So let's say we have this car, we have gravity pulling straight down, we have the normal force going up off at an angle like that. Now we're going to say, how fast can we make it around this turn? We'll say our mass is still 900 kilograms, our radius is again 500 meters, and we'll say our angle, right, the angle that this turn is banked at is 15 degrees. And so we want to say, what is the maximum speed that we can go around this turn, even if there is no friction? So again, we're saying the coefficient of friction is 0. So with this information, how fast can we make it around this turn, even with no friction. Okay, so we have our free body diagram here, right? We have our gravity going down, we have our normal force going up off at this angle here. And is there anything else we need to write? Again, there's no friction, so there's no frictional force in this case, so this would be it, right? These are our only two forces. Now, in the past, when we've had objects on these slanted surfaces, I would say it's a good idea to tilt the coordinate system, right? But why did we do that? The reason was because usually we have our object sliding up or sliding down this ramp. In this case, though, what is the direction of the net force of our object? The direction of this net force as we go around this turn is going to be pointing straight in towards the center of the turn, which would in this case be drawn straight to the right. So the net force actually is pointing in this direction. I don't quite want to draw it on my free body diagram, right? You just want to draw the individual forces on there. But just to show you the relative directions of this kind of stuff, the net force actually acting on it, right? The centripetal force acting on this car is pointing straight in towards the center of the turn. So in this case, I would say the easiest thing to do is to not tilt your coordinate system, right? I know we're on the slanted surface, but don't tilt the coordinate system because the car is not sliding up or down this ramp, right? It's not actually, it's just going around this turn. It's staying at this same height and it's curving to the right. Okay, so with that, let's not tilt our coordinate system. Let's make sure we set up, understand this angle here is also theta. Again, you can do the geometry, you can convince yourself of that. Again, you can kind of visualize it the same way as this opens up here. This angle is going to open up in the same way. So the angle between the normal force and the vertical will be the same as the angle between the road and the horizontal. So with that, let's set up our equation and let's figure out how fast are we able to go around this turn. So if I add up all my forces in the x direction, what do I get? My forces in the x direction, there is an x component to the normal force. So that's Fn times, in this case, with this angle theta here, this coefficient here, it's opposite the angle right this side. So it's Fn times sine of theta equals mv squared over r, right? This is the only force acting in the x direction, right? Gravity is just pulling straight down. And so we know that our net force is the centripetal force. This is mv squared over r. So this is my F equals ma. Right here in the x direction, we can look at this, sum up all my forces in the y direction, and what do I get? What's the component in the y direction? Well, it's F n cosine theta minus mg equals 0, right? There again, there is no acceleration in the y direction. The car is not jumping off the road, it's not falling into the road or anything like that. So we have Fn, of course, this allows us to write the normal force is equal to mg divided by cosine of theta, right? So now with this, right, what we're solving for is this v. We want to see how fast we're able to go around this turn. So plug in our normal force into here. We have mg sine of theta divided by cosine of theta equals mv squared over r. This, of course, is going to be tangent. The masses will cancel, and so what we end up with is this. Tangent of theta equals v squared over rg. We know what the angle is. We know what the radius of the turn is. The mass of the car cancels out. We did know it, right? We were told that. And we also do know what this g is, right? We can assume that we are driving this car on Earth. So let's solve for this v, and we can say this. We have v equals square root of r times g times the tangent of theta, right? We plug all our numbers in, and what we get is a speed of about 36 meters per second. So here we can see when we bank these turns like this, we have this normal force is going to help push us around. So even if we don't have any friction, so if it's a nice slick day out, maybe it's ice, we have some ice on the road or something like that, we're in the middle of winter, it is possible to go around these banked turns even with little to no friction. I would not suggest trying it, but it is in theory possible. You can see this does kind of illustrate. This is the reason why these turns are these roads are banked, right? It allows you to maintain a higher speed on the highway and not actually slide off the road or anything like that. Okay, so this is obviously one way we can do it. However, let's go ahead, let's take a look at this again. This is going to come up on your homework. Let's take a look at what happens if we do add friction in. Makes it a little bit more complicated. Banked turn with friction. So then in this case, let's redraw this free body diagram. I'll have to make it a little bit bigger. There's some more forces going on. I'm going to make sure we are able to see everything. I'm not going to put any numbers to this. This is a homework problem that I'm going to have you do. I'm going to have you figure out a banked turn with friction, how fast you can go around that, but I will start it for you, right? So this will be very helpful for the homework assignment that I'll give you at the end of this chapter. So here's what we have. We have a banked turn. It's banked at some angle. We again have our car going around this turn. Again, I'm just the way I'm drawing it, you can visualize it however you want, but the way I'm drawing it again, this car is going into the page, it's going away from us. This is the back of the car, and it is again turning towards the right. Okay, so now that we have added friction in, let's go ahead, let's draw our free body diagram, and I'll set up the equations. I'm not going to put any numbers to it, but I'll kind of get you started on how to go about solving this problem. Okay, so we have this case. Obviously, we know we have mg, we have our normal force, but then we also have friction in this case. And now the trick that we need to figure out is what is the direction of this frictional force. So we know two things about the direction, right? It is parallel to the surfaces that are sliding up against one another, and it opposes that sliding motion. So here's how you can visualize it. You might think, okay, is it going? It's got to be parallel to the surface, so it's either going up or down this slope, right? It can't be going, off at some angle or anything like that. It has to be parallel to the surface. So you can think to yourself, is this friction pulling me up or is it pulling me down, right? So the way to visualize it is like this. Imagine the frictionless case, right? Imagine I'm taking this turn and I'm going too fast and I do not have enough friction, right? Or there is no friction whatsoever, right? Which way does the car start to slide? It slides up the hill, right? So in this case, right, if I'm going around this turn and I'm going too fast, the car will start to drift up wider and wider, and will start to move up and slide off the road in that direction. So now, if that's the frictionless case, if I add friction in, friction is going to oppose this sliding motion, and so the frictional force will be pointed in this direction down the hill, right? So these are my three forces, and now we can set up our Newton's second law equations. Okay, so let's make sure we get our angles right. This angle here, again, as we said before, this is theta, but also this is theta as well, right? So here's my three different angles that I have to deal with, right? I mean, they're all the same angle, but just as far as where we can label them. So with that, we can do everything in terms of this angle theta, and now we can start breaking these down into our x and y components. So before we had just the normal force, had an x and y component, gravity was just in the y, but now friction, as we can see, also has both an x and y component. So let's sum up my forces in the x direction. What do I get? Well, we start as we had before. We have F n times sine of theta, right? We want this component of that. Now also in the x direction, we have plus F times which component times cosine of theta, and this must be equal to, let's make sure I don't run off the page, mv squared over r, right? So again, I'm still not tilting my coordinate system. I'm still saying, okay, I'm accelerating this way, so I'm going to set up my standard coordinate system. So we have f n sine theta plus f cosine theta equals mv squared over r. Let's look at these in the y direction, and we have this. We have f n cosine theta, right? Obviously, this is in the y direction, right? So adjacent to this angle, f n cosine of theta minus mg, right? And don't have to worry about any angles there, just mg straight down, and then minus, right? Friction is also pulling me down, right? It's pulling me down the hill, so it's pulling me to the right, but it's also pulling me down. So we have then minus f times sine of theta, and this is going to again be 0, right? So again, we also want to make sure we keep track of the fact that the frictional force is equal to mu times the normal force, right? So now if I give you some sort of combination of these variables, let's say I gave you, I don't know, the coefficient of friction, the angle, um, and I think the mass cancels out, but and then the mass of the car and the radius of the turn, you could then start solving for the speed, right? So these would be your three equations. It would be a lot of algebra. Again, will be one of your homework problems, but make sure you understand how to set up this free body diagram, and you should be okay with these types of problems.